This is the first application for integration, which corresponds to area and center of mass. The focus is going to be on area, but there will be an example of how to find the center of mass of an object also coming up in the first case. You should read this first page at your leisure. The highlighted parts correspond to how you integrate, and particular area is integral is the area under the curve between A and B. And the first highlighted part is if you were finding the area between two curves, F and G. The second, third highlighted parts correspond to the x and y coordinates of the center of mass of an object formed by two curves. So let's jump right into it and start doing some examples. I've already done this first one, but I want to talk you through it. On the left side, I have a sketch of the situation. We want to find the area between the curves y equals 2x and y equals x over the interval from 0 to 3. The y equals 2x function is the higher one, the one on top, and y equals x is the lower one. It's got a smaller slope. And so here we have one function on top, one function on bottom within the region from 0 to 3. So I am going to integrate from 0 to 3 the topmost function minus the bottommost function. So the top function is 2x, bottom function is x. That happens to simplify to just 1x, which is x squared over 2 after you integrate, and evaluating x squared over 2 from 0 to 3 comes out to just 9/2, or 4.5 in decimal form. Either format is fine. But then the problem also asks for us to determine the center of mass. So let's find the x-coordinate first, which is done right here. According to the formula, the x-coordinate is given by 1 over a. We just got a to be 9/2, so the reciprocal is 2/9, times the integral of x times the difference between the top minus bottom functions. So using that, I've got the integral of x times the yt minus yb, which we had just found is also x, and that's where the x squared came from. Integrating x squared is x cubed over 3. Evaluating that from 0 to 3, you've got 3 cubed over 3, which is 3 squared, and that's going to be 2/9 times 9, which simplifies to just 2. And so here's our x-coordinate. The y-coordinate is going to be 2/9, so 1 over the area. The integral from, and this should be 2 integrals. And that's because integrating with respect to y, you're going, instead of top bottom, you're going right left. And I could see that the rightmost function changes depending on where I'm at. So when I am below y equals x, my rightmost function is y equals x. But when I'm above y equals x, my rightmost function is x equals 3. And so here, the bottom portion below the red dashed line in the graph is integrating from 0 to 3, and this is 0 to 3 according to the y-axis, by the way. So 3 is where that dashed line is. So in the region below the dashed line, I have y times the rightmost function, which is x equals y, minus the leftmost function in that region, which is going to be x equals 1/2 y. So that was solving for x in the y equals 2x function. That simplifies to 1/2 y times y, which is y squared over 2. And the second integral is going to be using the rightmost function of x equals 3 minus the leftmost function, which is the y equals 2x, but solved for x, so x equals 1/2 y. And you're still multiplying by the y up front. So when you multiply through and you integrate, you get this next line here. And as you evaluate that, the first part from 0 to 3, the second part from 3 to 6, it simplifies to 3. Which means our center of mass is at the point 2, 3. So that is the first example. It's showing both types of applications, the area in a region and the center of mass of that region. So just to visualize it, by the way, center of mass, here's x equals 2, and 3 is right about there. So this point is the center of mass. If we were to have this object and balance it right there, it would balance. Let's take a look at the second problem here. It asks us to find the area bounded above by y equals e to x and below by y equals x squared between the sides of x equals 0 and x equals 1. So I've got a little sketch over here just of what the region looks like. So we want to find that shaded region. This again is a top over bottom. You could do right minus left, but it would be a more complicated setup. Top over bottom is going to be the more direct one. So setting up our integral, we want the area, which is the integral between 0 and 1. The top function is e to the x. The bottom function is x squared. And integrating this, integral of e to the x is e to the x, and integral of x squared is x cubed over 3, which, evaluating this from 0 to 1, comes out to e minus 1/3 when you evaluate 1, minus when you evaluate 0, e to 0 is 1, minus x cubed over 3 at 0 is 0, which means our answer is e minus 4/3. Problem 3, I started a little bit, but I'll explain it in a moment. We want to find the area of the region enclosed by the parabolas that are given here. I've got a sketch of that in the bottom left. The top function is the function with the negative x squared, and the bottom function is the one with the positive x squared in it. To know the region that it's enclosed by, you need to figure out for what x or what y do these two functions equal to each other. Since they're both written in a y equals form, I set one y part equal to the other. So x squared plus 12 is y, so I substitute that into the right equation, which gives me this first line. Then getting all the terms on one side, I've got 2x squared minus 10x plus 12 equals 0. Dividing by 2 gets me line 3. And then that happens to factor nicely into x minus 2, x plus, or x minus 3, which means that these two functions intersect at x equals 2 and 3. So that's how I figured out the region that we're interested in. Now I'm ready to actually integrate. So this is integrating from 2 to 3. This one would actually be the same whether you integrate top, bottom, or right, left, except since it's already written as y equals, you've already solved for y. It would be a little more complicated solving for x, just because you have the squared terms. So Continuing with integrating with respect to the x-axis, the top function is negative x squared plus 10x minus the bottom function, which is x squared plus 12. This simplifies a little bit to minus 2x squared plus 10x minus 12, which when you integrate, we get negative 2/3 x cubed plus 5x squared minus 12x. Evaluating that from 2 to 3, evaluating at 3, you get negative 2/3 times 3 cubed. Now the 3 cubed divided by 3 is 3 squared, so you've got negative 18 plus 5 times 3 squared, which is going to be 45, minus 12 times 3, which is 36, minus, now evaluating at 2, we've got negative 2 to the 4th, which is 16/3, plus 5 times 2 squared is 20, minus 12 times 2 is 24. And as we keep simplifying, I see that negative 18 minus 36 is negative 54, plus 45 is negative 9, minus, and inside the parentheses, the 20 minus 24 is negative 4, which is negative 12 over 3, or negative 28 over 3. So getting a common denominator of 3, that negative 28 is going to become positive with the negative sign outside. And the negative 9 becomes negative 27 over 3, which means our area is just 1/3. And that brings us to our final problem, which starts off similarly, and that is we want to find the area of the region enclosed by these two functions. So I need to find either for what y or what x, are they the same? In this case, since y equals x minus 2, I subbed x minus 2 in for the y of y squared and the right function. So that's the first line here. From this point, I squared out the x minus 2 squared, got all the terms on one side, saw that it factored nicely, and that the x's are negative 1 and 7, for which these two curves intersect. I've got sketches of them in the bottom left here. The top function is the y squared one, and the bottom function is the y equals x minus 2. The y is not negative, even though it looks like a negative sign, but that is the bottom function here. This one is going to be integrating, easier to integrate right minus left. So that means I'm integrating with respect to y. I know that x is negative 1 to 7, so I need to find the corresponding y values. So at x is negative 1, y is negative 3. I just plug negative 1 into either of those equations. And when x is 7, using the first equation, y equals 7 minus 2 is 5. And so those are my two bounds. So I'm integrating negative 3 to 5. The rightmost function is x equals y plus 2, solving for x. And solving for x in the second function, I've got y squared minus 11 over 2. So now we could simplify this a little bit. I see that we're going to have a negative 1/2 y squared plus a y. And then we have 2 minus a negative 11 halves, or 2 plus 11 halves, which is going to be plus 15 halves. And this integrates to negative y cubed over 6 plus y squared over 2 plus 15 halves y. Evaluating, we've got negative 5 cubed, which is 125 over 6, plus 5 squared over 2, which is 25 over 2, plus 15 times 5, which is 75 divided by 2, minus, now evaluating y at negative 3, we're going to have minus negative 3 cubed. Negative 3 cubed is negative 27, so with the minus sign out front, this is positive 27/6, plus negative 3 squared is 9 halves, minus 15 halves, and I already brought the minus sign out from the negative 3, so that's going to be 45 halves. So now I'm going to combine the terms with common denominators. So the negative 125 over 6 minus the 27 over 6 is going to be negative 152 over 6. And then the fractions with a common denominator of 2, we've got 25 plus 75 is 100. Inside the parentheses, we have 9 minus 45 is negative 36. But there's a negative sign out front, so that's going to be positive 36. So this is going to be 136 over 2. And let's divide. Let's see. The first one is, if I factor out a 2 on top and bottom, I'm going to have minus 76 over 3. And the other fraction is going to become 68. Putting 68 with a common denominator of 3. Let's see, negative 76 plus 68 times 3, that's going to be 180, and it's going to be 204 over 3. And when we simplify this, we've got 128 over 3. And so here you've got a collection of different types of examples. Some that you integrated with respect to x, some you integrated with respect to y, some you had to consider it as a single integral, and some as double integral. And you even got to see in problem 1 how you could find the x and y coordinates for a center of mass. Good luck.